fill when I do the introduction for the day, but I'm very excited to introduce our speaker today, Dr. William Gross. He is an assistant professor here at the college and has a joint appointment here in neurology and anesthesiology. He got his MD and PhD concurrently while at MCW, his PhD in 2010, where he studied under Dr. Jeffrey Binder and the focus was on an emphasis of neuroscience and MRI, where he looked at using fMRI to improve outcomes and surgical treatment of TLE and continues to publish in this area. After getting his MD, he began a fellowship in anesthesiology and completed that in 2018, and then that was his residency, and then a fellowship in neuroanesthesia, which was completed in 2019. In 2020, he got additional training as being a clinical research scholar program as part of a grant that he received at KL2, which is supported by the NIH, and work which we will hear about a little bit more today. Many of his publication topics span topics across functional imaging to investigating the induced effects of anesthesia on resting state connectivity and perceptual cognitive functions. He is also very active in education. One of the things that I find most interesting about Bill is his ability to take really complex ideas and kind of boil that down into something that's more easily understood and digestible. And in spirit of that, he took over as the director of the medical student anesthesiology clerkship this last October. In the spirit of keeping with fun facts, when he's not busy with work and research, Bill shares and spends his time sharing his love for games with his kids and is the dungeon master for his children's D&D games. And he said that a good tip is that you have to know the rules, but you also have to be good at improvising, which actually sounds a lot like conducting a research study. So with that, I'm going to turn it over to you, and thank you for taking time to speak with us today.
Interesting segue. Thank you. Thank you for that introduction. I'm going to start sharing my actual slides here. One second. Click, click, click. Okay. You can see the slides okay? Awesome. So thank you for that introduction. Thank you for inviting me. I feel like I have a secondary appointment in neurology, but I feel like probably a lot of you don't know me. I kind of get around in different places in different ways. My research is primarily focused in neurology, so I've worked with a lot of you in the research side. Clinically, I'm an anesthesiologist in the ORs, and I focus on neuroanesthesia. So I've worked with many of you who do procedures in the ORs as well. But today I'm going to be talking about some of the research studies that I've been working on. The focus is going to be on trying to understand this concept of grounded cognition. What are the theoretical motivations of this, and then the recent evidence that we've collected kind of supporting this idea. I have no current disclosures I can think of. I am actively looking for disclosures. If anyone has any tips, I'm happy to think about them. So again, in brief, I'm gonna kind of talk about some background of our conceptual system, and then I'm gonna present the data from this recent study that we've done. So, language and our conceptual system. Language is, as I'm sure most of you on the call know, language is one of these fundamental things about our brain's functioning. It's not just responding to words that we hear. Dogs can do that. It's not just saying words. Parrots can do that. One of the things that fundamentally underlies language is our conceptual system. And our conceptual system, meaning we have this ability to create these abstract concept symbols in our head, and we can manipulate those. And that abstract symbol manipulation is something that I would argue is pretty uniquely human. It's one of the things that makes us human, makes us be able to do all the cool things that we do. I would also, as a complete aside, say that the way that we handle these abstract symbols in our conceptual system is also what underlies consciousness. That's a whole different topic. So our understanding of the conceptual system, where did that come from? So like most things in neurology and neuroscience, it all started with analyzing deficits that we saw in patients. And so Elizabeth Warrington here published one of the seminal papers on semantics. In this case, it was studying a group of patients that have semantic dementia, and a group of patients that had relatively isolated semantic deficits, and had this, frontotemporal dementia syndrome. So with atrophy of the temporal lobes, these patients started losing semantic processing. And so just some examples of things the patients would produce. When they were asked to draw a duck, for example, they draw a duck with 4 legs because they would forget that ducks have 2 legs. And these facts, same thing in their language system, they would start forgetting specific words and go more general. And the real specific deficit that they had was they started forgetting facts about things. They started their conceptual knowledge started becoming degraded. And that was in conjunction with the atrophy of their temporal lobe. And so there was this association produced of, okay, well, the temporal lobe must be where the conceptual system is located. And this eventually led to what we call the hub and spoke model. Taking directly from these this patient evidence, it seemed like that anterior portion of the temporal lobe is the critical area for these concepts. And it was this whole conceptual system was conceptualized as basically there are abstract symbols created in this conceptual area of the brain. And then that area interacts with the other areas of the brain, the perceptual areas, and is able to receive from them. If you see a picture, the visual system activates this hub in the anterior temporal lobe, and that activates the concept. And then that concept can then coordinate activity across the brain. So this is the hub and spoke model, one of the prominent models of conceptual retrieval. What's the alternative to this? Well, around the same time these patients were being studied, Antonio Damasio put forward a differing viewpoint on the general organization of the brain. And it's based on a couple kind of simple observations of how the brain works. We learn things by experiencing the world, right? So I learn everything from when I'm a baby just from my perceptual experiences, and I have to learn it in an unsupervised way. I'm not necessarily born with English in my head. I have to figure it out through my experience with the world. And so kind of thinking about this in the way that the brain is laid out. So if I, like taking our visual system as an example, if I see something, I get an activation on my retina that activates primary visual cortex. I get a primary representation of the stimulus coming in from the world. And then we know that there are these association cortices related to that create abstractions on top of that perceptual experience. For example, in the extreme of the hub and spoke model, you wouldn't say that the direct retinal activation goes straight to the anterior temporal lobe, activates a semantic representation there, and then that coordinates everything. No, there are these intermediate representations, abstractions that get created. And if you look at the design of the brain, like the design that has motivated artificial neural networks in computational studies, there's this progressive hierarchical abstraction where abstractions then get combined into further abstractions, the abstractions get associated with each other as they are co-activated, and the co-activation creates connections between them. And it turns out that this hierarchy is very similar to how it appears the brain is laid out. And using this hierarchy, we can create abstract concepts without there needing to be a conceptual area. The concept is actually distributed across the entire network. And it's not that the highest order, the highest level abstractions are the ones coordinating the entire network. The network can kind of function independently based on which areas are activating, which areas are needed to be activated, and certain of these abstraction layers, which he called convergence zones, can be activated in different times. So we have this kind of hierarchical model of the conceptual system where there are layered abstractions, several layers, they can activate depending on the context, versus the hub and spoke, where the hub, this central amodal area, is coordinating all of the activity. This hierarchical model has led to theories that we call grounded theories or grounded cognition. That meaning that the store of our conceptual system is fundamentally related to our perceptual system. It's not that the abstract symbols that we are using aren't arbitrary amodal symbols. They are symbols that are fundamental to the perceptual foundation that they were created from, because that's how they were created. So if we were going to implement this in the brain, where would it be? And there's been plenty of work looking at where the conceptual system is in the brain. This is a very nice paper by Jeff Binder looking at a meta-analysis of 120 fMRI papers looking at semantic activation. And you see that there are various regions all across the brain that activate due to semantics. And you can see, to my eye, it looks like you have kind of, the major perceptual areas, you have the major visual areas, major auditory areas, and then the semantic system basically takes up the space in between. There's this huge swath of cortex that kind of maps different areas together. And we know these areas activate during semantic tasks. So are these areas a large hierarchical network that's storing a distributed representation of concepts? Or the hub and spoke model might argue these areas are the spokes, but their activity is all just coordinated by that one hub. If you take out that hub, this network completely falls apart. It's being driven by that hub, which they would offer support from the patients of, if you destroy that hub, you lose semantic activation. Okay, so that brings us to the question at hand. So we have all these fMRI studies that have shown this distributed network of semantic areas. How do these areas actually interact? Is it that there is a hub that is activating, that is driving the activation in all the other areas, or is this acting more like a large interactive network? And related to that, if we change semantic task demands, is that going to change the activation through this hierarchical network? If this was a amodal hub region, we would expect that it should activate to the concept regardless of the task demands, because it's the highest level abstraction. It needs to activate regardless of what sub-components of the concept need to activate. Whereas in the hierarchical network, the different task demands should be able to modulate, because you don't necessarily need to activate the entirety of the network just to get certain semantic features out. So we decided to try to answer these questions using ECOG, electrocorticography, instead of, for example, fMRI, which we have much more experience with here. The reason why we picked ECOG was because the timing and spatial location of ECOG is amazing. We can show very precisely in very specific areas what activation is going on. One of the classic problems with ECOG studies is we say the spatial resolution is high because where we measure, we know where we're measuring. One of the big problems is that ECOG is an invasive recording. It's recording from the brain surface or from depth electrodes placed into the brain. And so it's generally not the kind of thing we can just walk up to someone and do. So we're generally, in the past, most ECOG studies have only used clinically placed electrodes. So if someone's coming in for epilepsy monitoring, they're getting electrodes placed anyway for epilepsy monitoring, we will record off of those electrodes that are already placed and then do our study. The problem is that ends up with a very haphazard, not random, but variable placement of these electrodes. And it's very hard to get specific areas recorded. And especially in this context, recording multiple specific areas simultaneously to look for timing differences. So we wanted to find a way to record ECOG in a specific way that we wanted to. And the other thing I'll note is that a big difference that we added as well is almost all of these previous studies have used pictures as their stimuli, which they're great stimuli. Some of them also use names, words, but it kind of fundamentally confounds visual processing with semantic processing. So another manipulation that we added to this study was we added characteristic sounds of objects, very recognizable sounds, instead of having a visual display. So these are some of the examples of the stimuli that we used in this task. There were 9 pictures and 9 sounds that we presented multiple times in multiple ways that I'll show you in a second here. The pictures were all common everyday objects. There were different categories, animals and objects, and they're all for these analyses. I'm lumping everything together. They were all black and white because we were asking about color. They were all normalized in the size and overall brightness and etc. The sounds I'm going to play. Hopefully it'll work. I'm going to play a couple examples of a sound. Here's one example of the sound. Did you guys hear that? Can you identify what that was?
Frog.
A frog, that's correct. Here's the second one. Anyway.
A socket wrench?
Socket wrench, that is correct. So again, 9 sounds, 9 pictures, all of common objects, common concrete concepts. They were all perceptually normalized so that they would be as even as possible. And before doing the task itself, I ran through all of these stimuli with the patients beforehand. So they were all familiar with them. They shouldn't be confused. There shouldn't be novelty effects. These were all familiar stimuli to them. Again, like I said, 9 pictures, 9 sounds. There were 16 blocks that we did, and these 16 blocks covered 4 semantic features, which I will explain here in a second. The basic task, not getting too much into the details, was all of the feature judgments were blocked. So they were making the same judgment over and over again, just to try to reduce switching costs. They would be fixation, and then the stimulus would play at a very fixed timing. Because we were very concerned about timing, we used photodiodes to actually measure the stimulus presentation on the monitor. There was a whole complex thing we had to do to actually measure the timing of the sounds, which is very hard, probably why nobody uses sounds. But so that was the basic paradigm. So what were they doing? They were making these semantic judgments. So we showed them a picture or a sound, and then in blocks, the patients had to answer one of these questions, yes or no. And they just kept answering yes or no to a series of stimuli, and then we move on to another question. The questions, there were 2 questions per semantic feature. And so, for example, for color, is this sometimes colored brown? Motion, can this go faster than you? And they answered each of these questions for each stimuli. So you can see here, it's kind of this, this factorial design where we had color, sound, and motion features for 9 images and 9 sounds. And I want to make sure we don't get confused here, because I'm going to be trying to stay consistent in my language, calling these stimulus modalities, meaning they were actual pictures and actual sounds that we presented, versus the semantic features, meaning the question that we asked. So there was a semantic feature question, sound, meaning is this loud? And we asked, is this loud, on both sound stimuli and picture stimuli. So just try to not get confused on that. I will try to call these features and these modalities. But there was also a 4th manipulation. I'm not hiding it here for any nefarious purposes. I'm just trying to keep the data simple. And I think these show characteristically the effects that we found. So how did we actually do this? So like I said, we wanted to place these grids specifically where we wanted them. So our neurosurgical colleagues, Wade Mueller and Max Krukoff, are first of all extremely kind individuals and very patient individuals. And if you know anything about surgeons and the operating room, everything is extremely high strung. And they let me do this experiment in the middle of their operations. So this was during awake craniotomies, where the patient is completely awake and we're doing a tumor surgery, in this case, in the left temporal lobe, because that's the only way that we can monitor language during the surgery. So we do the surgery in the left temporal lobe, and during the surgery, we're performing neuropsych testing while their brain's exposed. So you see, this is me doing the task right here. The patient is strategically located behind my arm here, so we can't see their face. And this is all on the non-sterile side, on the anesthesia side. On the other side of the drapes, on the sterile side, we have our surgeon, Dr. Mueller, and you can see here all these little tails of all the grids. We had 3 high-density grids placed in specific regions, specifically the superior temporal gyrus, middle temporal gyrus, and down on the inferior temporal lobe. And in total, we had 192 electrodes that we placed. We placed them after the brain was exposed. We placed the grids down, did the task, and then immediately removed them. So because we only placed them under direct surgical guidance for a temporary period of time, risks of like hemorrhage, infection, those sorts of things were minimal. We expected. Nothing has happened so far, thankfully. And we were able to do our experimental paradigm exactly as we liked in this kind of environment. So this was a very difficult thing to coordinate, and I'm very appreciative to the neurosurgeons for working with me through this. But it's wonderful that we were able to accomplish it. So how do we analyze this data? We collected this ECOG data, off of these 192 electrodes off of the surface of the brain. We're recording at 2000 hertz. The way that we're analyzing it, we're trying to get high gamma power. If you're not familiar with these types of analyses, high gamma power is this very, very high frequency activity, and it's associated with local neural activity. There are all these other low frequency waves that are associated with different networks and different states of the regions of the brain. The very, very high frequency activity is relatively localized to local neural activity. So we bandpassed 70 to 200 hertz, did a Hilbert transform to get the instantaneous power. You can see here, up here on the top right, is a raw signal from one of the leads. And then this is band passed 70 to 200 hertz to get the high frequency activity from there, take out that low frequency activity, and then do a Hilbert transform. And this gives us the absolute instantaneous power. And you can see this is a single trial. And after stimulus presentation, you see this big increase in activity. The data quality on ECOG, in my experience, relative to using other modalities, is amazing. The amount of power and precision in this data is wonderful, and we're able to show all sorts of interesting things. So the data that's a single trial right here. The data that I'm going to be showing you here, each time course that I'm showing you is going to be an average of 18 trials, because there were 9 stimuli and we asked 2 feature questions for each feature, so that it ends up being 18 trials that we're averaging over. Okay, so now present you some results. These are all my caveats of, I'm going to try to give you the best interpretation that I can of all the results. There's a lot of data, so I would love to go through all the details, but I would lose a lot of you, probably including myself. And I'm going to be showing you big pictures. I don't want you to get caught up in all the data. I'm going to be trying to focus in on kind of individual points as we walk through the story. So the first question that we had was, are these modal regions, are these spoke regions, are these are the non-high level representations driven by this amodal hub? Is this single high level representation driving everything? So to answer this question, let's step through the picture data. So we have the data from where we show pictures and then have them make semantic decisions, and when we play sounds. So this is only the presenting pictures and having them make semantic decisions. So you see over here, this is the average high gamma activity after stimulus presentation, which is there. And I have each of the average features, color, sound, and motion graphed in a different color here. So these are all the leads that activate very early, very consistently, with no modulation by task. And so you see that we have this nice sweep of activity across the lateral occipital lobe, and then also this very early undifferentiated activity in parahippocampal gyrus. So we're associating this with the initial stimulus. They're looking at pictures. They have to identify the picture before they make a decision on the picture. So this is the image identification activity, is how we're interpreting it. And you see it starts, in this case, around 125 milliseconds, which is very in line with previous literature. You see here a couple of citations. The Thorpe was a EEG study. Liu was actually a SEEG study. Chen was actually another ECOG study. All 3 of these showed early activity on the order of 100, 150 milliseconds that differentiated based on the stimulus type. So they're on the order of 150 milliseconds, we are getting actual stimulus recognition going on, and it's not modulated by task. It's simply the recognition of the picture. Okay, so that's the initial activation. Now, if we broaden out, this is the kind of overall network that we see after that image presentation. Again, in blue here, you have the same dots. These are the electrodes that were associated with that initial burst of activity, undifferentiated. And then those are what I'm calling the low-level representations of the stimuli. And then we have several more electrodes that start popping up later that have higher level representations of the stimuli. And those go through more anteriorly into the middle temporal gyrus, up into the angular gyrus, and in the inferior temporal lobe. I'm going to walk through those specifically here for you. So those high level representations. So we see this is one patient, this is another patient here. You see we have this big cluster of activation in the middle temporal gyrus, in the angular gyrus inferior parietal lobe. And these are the average responses in both of those places. All these electrodes have pretty characteristic similar activations to these. The activation starts around 300 milliseconds and is not really differentiated by task. So I would say this is consistent with the high level representations. This is the very abstract semantic representations that are getting activated. They're not being modulated by task because, again, these are the high level, they don't modulate by what modality you're talking about. These are kind of the core concepts. And they're distributed in, if you remember the cerebral cortex figure from before, they're distributed in these areas that we would expect. The middle temporal gyrus is a big semantic area going up into this, these inferior parietal areas. Angular gyrus are also big semantic areas. So we're getting this core high level abstract concept activation around 300 milliseconds, not differentiating by semantic task demands. So this is consistent with, okay, these are kind of the core semantic network. So now, if these are the high level representations and these are activating, and our argument, if we're taking the perspective of the hub and spoke model, the hub and spoke model would say, okay, the hub, that's kind of the core semantic network, the high level semantic network, those areas should be driving activation everywhere. So you shouldn't be able to see areas modulating by task before 300 milliseconds, for example. The thought process is, okay, I'm showing a picture. So you have the visual activation. That visual activation kind of goes straight up to the core semantic regions, activates the concept in the semantic regions, and then that activation can then coordinate activation in other areas if it needs to. If it needs to activate other perceptual cortices based on task demands, it will do that. But temporally, that should happen after 300 milliseconds. Everyone following me? So the question here is, are there semantic areas that modulate based on semantic task demands that happen before 300 milliseconds? And the answer is a resounding yes. There are all sorts of areas that activate very early prior to 300 milliseconds that strongly modulate to task demands. Here are a handful of them. This primarily inferior temporal set of regions starts activating right around stimulus recognition, right around 150 milliseconds, and is primarily driven when the subject is making a color decision. And remember, each of these curves is comparing the exact same stimuli. So these are all pictures. And so they're seeing the exact same, literally the exact same pictures for this, and this. The only difference is what they're being asked to judge it on, the semantic feature that they're asked to judge it on. When they're asked to think about what color is this thing usually, because they're black and white photographs, that creates activation in the inferior temporal lobe. When they aren't, they still get some activation there, but not nearly as much. Same thing over here. This activation in the superior temporal gyrus only happens to sound and motion judgments. And when they're making a color judgment, that area does not get activated. And the area starts activating around 250 milliseconds before the high level representation. So this shouldn't be being driven by the high level representations because it's happening prior to that. Also of note, if you're thinking about how this hierarchical network might be implemented, I said different limbs can get activated differentially based on the needs. It also has to be implemented in a physical network, right? And so the communication between limbs, the distance on that hierarchical tree should modulate the processing time. So for example, we're showing a visual stimulus. When we ask about visual features like color, the differential activation happens very quickly because we're presenting a visual stimulus and then we have to activate visual concepts, which in the hierarchical tree are immediately adjacent. So they should be able to be activated very quickly. Whereas if we're showing a picture and we ask about sound modality, we might not have to go all the way up the hierarchy to the core concept, but we have to go up to at least some mid-level convergence zones. We have to at least activate some higher level abstractions than the visual cortex to be able to activate the sound cortex. So that activation is delayed when we're asking about modalities outside of the modality that we're presenting in. Makes sense so far? So, slam dunk, we proved everything, no questions. And I hear some of you in the background might be saying, well, okay, you showed that these, these heteromodal, however you want to describe them, these mid-level representations activate before the high-level representations. That's all well and good, but what about that parahippocampal activation? I mean, that, and if you actually look back at, for example, that Chen paper that I referenced that also found early parahippocampal activity, the senior author on that is Matt Lambon-Ralph, who is the primary proponent of the hub and spoke model. And he actually called this parahippocampal activity the hub. So, okay, I showed the middle temporal gyrus and angular gyrus and all those other regions activate later. Their high level representation activates later. But what about the parahippocampal gyrus? Maybe the parahippocampal gyrus is the hub. Maybe that's the thing that has all the core concepts that's coordinating this whole thing. It activates early. It doesn't differentiate. It's not clearly a perceptual cortex, right? Did I just replicate the spoken hub data? So one issue with doing this is the issue that I said before of all of this data is collected in making semantic judgments on pictures. What if we didn't use a picture? So the next question is, okay, so we've shown, there are lots of regions that activate very early differentially to semantic features based on task demands. We still haven't ruled out the parahippocampal gyrus. That's the elephant in the room. Is that the phrase? It's an anterior temporal structure. We know it activates early. It's already one of the possible hubs. So is the parahippocampal gyrus the hub? So now let's switch gears to sound stimuli. So like I said, everything that's been done previously has been done in pictures. Not everything, but the majority of things previously have been done in pictures. What if we use these natural sound stimuli? So you see here, same idea. This is after playing the sounds, you see activation as you would expect along the lateral aspect of superior temporal gyrus, activation near primary auditory cortex. And it's slightly more delayed, 160, 180 milliseconds from the initiation of activation is a little delayed relative to the visual system. Sound, the auditory system in general runs a little bit slower. And it's spread over time fundamentally because the stimulus is spread over time. But we still get a very robust initial activation to sounds. Interestingly, we also get this lateral occipital cortex activation. I'm not going to talk about that right now, but another interesting topic. So we get this, again, primary activation consistent with the stimulus that we're producing. But interestingly, there is absolutely no inferior temporal activation to characteristic sounds. So the parahippocampal gyrus can't be the amodal high-level concept representation, because you can identify characteristic sounds. You can make semantic judgments on characteristic sounds, and it's not activating to these stimuli. Now you might ask, well, I just went on a whole diatribe about how sounds are fundamentally not localized in time, right? They play out over however long, and the localization actually is probably going to vary. The temporal localization is probably going to vary based on stimulus, right? Some sounds you might get immediately, some sounds might take a couple more milliseconds. There's going to be variability there. That temporal variability could be washing out semantic effects, right? I mean, if there's a jitter in the semantic activation, then it's all going to average out to nothing. So maybe the semantic activations here in the parahippocampal gyrus are being washed out by temporal jittering, right? So what if we went stimulus by stimulus, each individual stimulus, and I took a window of the first couple hundred milliseconds after stimulus presentation, and I picked the maximum power value within that window for each individual stimulus. And then I averaged all those values together. So it wouldn't matter if there's any jittering between. If there's activation to these stimuli, that should show an average maximal activation, even though they're temporally jittered, right? Because anywhere in that window, if there's activation, it will all go together. So that's this. This is the average activation in the parahippocampal gyrus, maximally, the maximal power within the first 200 milliseconds for identifying sounds versus identifying images. And when I'm playing sounds to people, there is no activation in the parahippocampal gyrus early. There's some way later, but early activation in parahippocampal gyrus to sounds does not happen. It happens extremely reliably, extremely strongly to images. So I would argue the parahippocampal gyrus is a high-level node in the visual network. And so it activates early into visual stimuli, but it is not necessarily the highest level amodal semantic area. And then just to round out the data, so we have this low level activation when we present sounds, and then we get a very similar spread of activation within the semantic regions, within the middle temporal gyrus, inferior temporal gyrus. Again, similar kind of high level abstract networks. The high level areas to sounds tend to activate later, as I've explained. In this case, these are two subjects, 500, 600 milliseconds post stimulus is when these high level abstract areas come online. And then again, we see the same sort of earlier activation of areas that are differentially activated based on semantic feature. And as you can see, the earliest, most robust activation to sound stimuli comes when they are making sound judgments, which again makes sense with the hierarchical model. You will be able to activate these semantic sound regions faster if you're playing a sound than if you're playing, than if it's going in another area, or if you have to make a judgment about a different semantic feature that is more associated with a different perceptual modality, because you'll have to activate more intermediate convergent zones to get to that other modality. Again, all very consistent with what we had hypothesized with a hierarchical network. So finally, last question here is, so I've showed you that these areas modulate to semantic feature. Does this make sense from a grounded cognition perspective? It modulates, but from the grounded cognition perspective, we're saying that modulation is related to those areas being associated with the perceptual cortices that they were originally perceived and how they were learned originally. And so, for example, this is areas strongly modulated by color. And you see these inferior temporal regions that have a very strong color preference, and these are making color judgments to images. These are making color judgments to sounds. These areas, because they're semantic regions, will activate regardless of whether you're looking at a picture, looking at a sound. They will activate when you're trying to make color judgments. And the core area here in the fusiform collateral sulcus is consistent with other previous data we've shown that of where color perception is. The color knowledge is probably located in this collateral sulcus inferior temporal area. Sounds, again, this is making sound judgments to sound stimuli and making sound judgments on picture stimuli. And the core area that gets activated here is this posterior middle temporal gyrus area, which again is in physical proximity to auditory cortex. And in previous fMRI studies, that has been the dominant area that has activated semantically to sound semantic features and sound perception. So the data makes sense that yes, it looks like these regions are behaving as we would expect them in a hierarchical way. They're located near perceptual cortices. They're activating independently. They are not activating due to a central hub driving them. And just a note, other regions that modulate with color and sound, or sound and motion, which is interesting, particularly because motion is one of those features that is not necessarily tied to a single modality. So you would expect motion and sound, there should be areas that should represent both. So without getting into that too much, so we have a little bit of time here. So in conclusion, the data that we found with ECOG does not support the idea that there is a central amodal hub driving our semantic system. Rather, it supports the idea that there is a distributed semantic network that activates based on task demands, based on the perceptual features, and creates the concept in an interactive, distributed way, similar to how neural networks behave in a computational sense. We also found that the perihippocampal gyrus, while it is robustly activated during picture naming, picture perception, it seems that its role in identifying semantics is related to visual semantics, and it is not necessarily a amodal high-level representation. It's probably more like a mid-level representation, a high-level visual representation of stimuli. And we've supported that these convergence zones are arranged in a logical pattern, both in their physical location as well as their timing relative to what we would expect based on what the task demands are. So very quickly, a 1-minute plug for where are we going to take these? So this data is cool if you're interested in semantics and grounded cognition. This was great, but if you're not, yeah, okay. I just as a modality and as a paradigm, I think ECOG and these specific methodologies are extremely powerful ways of probing the brain, of getting very, very high quality data. And me personally, one of the things that I'm very interested in is clinical applications. Being a practicing anesthesiologist, I'm in the OR all the time. And if you know anesthesiologists, we love monitors. And there is no monitor, for example, for the language system. We have to do these surgeries awake because we have no idea what's going on in the language system. Imagine if we could build some of these intracranial systems recording and monitoring the language system while we're doing surgery. And the quality of the data, combined with the fact that these electrical systems can be made so small, so portable. Also, playing into that, if we rewind time last year, Max Krukov, one of our neurosurgeons we're collaborating with, gave a very nice grand rounds as well, talking about BCI applications. I think there are all sorts of awesome applications of recording from the brain, monitoring the brain, interacting with the brain through these types of recordings. So I'm very excited to be using this methodology. I think it's a very powerful methodology to use. And acknowledgements. I always feel weird with this because there's just so many people to thank. This is all obviously a huge team effort. Jeff has been my mentor through my PhD and so on. He's been an extremely good help. Manoj has been our primary electrophysiology reference and my electrophysiology mentor, because the electrophysiology part of this I'm still learning. Leo has done awesome work on a lot of these conceptual paradigms and has published several really nice papers. If you're interested in any of this, read all his papers. A heartfelt thanks to our neurosurgeons, because I know I'm very annoying in the OR, and their patience is amazing. And then several other people, Ahmed, are one of the neurosurgery residents who's been helping me. Dale Davis is an awesome tech that's helped me with a lot of the technical stuff. Linda Allen's just awesome. And Stacy's been helping coordinate some of the OR stuff. All of this work was funded by my KL2, and obviously lots of support from both anesthesiology and neurology departments. So that is what I have. I would love to answer any questions anyone might have.
Bill, Quinn Hogan here.
Yeah.
I know this is a very low throughput sort of scientific design, experimental design, but do you have enough observations to find if there's any heterogeneity between subjects, or how consistent is this design, how this layout?
Sure. So the interesting thing about the data is that it's so statistically significant that we can easily show statistical significance in individual patients. That being said, we know there is a large amount of heterogeneity in the semantic system. That's part of kind of what our lab does a lot. For example, when like Sarah mentioned, when patients go for like left temporal lobectomies for epilepsy surgery, for example, when cutting out the same area of cortex, some patients do fine, some patients have dramatic language deficits. And so one of the things that we've done with fMRI is map out these regions to try to see how much of that activity is in that area or not. Currently with this protocol, I have 2 patients, and we're planning to run 6 patients total, specifically to look at the amount of variability. With the 2 patients that I've done so far, the activation has been relatively consistent, actually. I mean, in a blurry sense, and the regional activation is pretty consistent. I'm sure, if I got down to comparing little differences in, this activation might be a centimeter this way, that way. But in these 2 patients so far, the data has actually been pretty consistent, which has been nice. We'll see where the future patients go. I expect there should be some variability based on what we see clinically.
Thanks.
Hey, Bill, really great talk. Really cool to see the data and sort of the 1,000-foot view of everything you're working on. It's really, really cool. I had a few thoughts as I was watching you talk and just kind of ideas, and we can talk more offline. But just a thought. So, yesterday I did a case of a patient with a kind of a deep-seated left dominant lesion, and it was basically came from and in the lateral thalamus, and basically pushed the SLF up and into the kind of medial portion of the dominant temporal lobe. But it was high and deep and posterior enough that a wake wasn't a reasonable option. So we did an occipital approach, and he came in with a hemianopsia, right-sided hemianopsia. So I figured coming through the left occipital lobe wouldn't commit any new deficits. But I'm thinking, as you're talking about sort of the visual processing things, how visual information is passed, from the occipital lobe where it's, first seen and then through the other systems. And I was wondering if it might add anything if you presented, at least for the visual stimuli, isolated in, like, for example, the right hemisphere versus the left hemisphere, and to see how it would, I would assume the timing would be different just on a processing perspective, if only the right occipital lobe receives the information and has to send it to the left versus the left occipital lobe. And I wonder if that may have implications to sort of the semantic processing network, et cetera. So just one thought. And then potentially with sound too, you could give it to just the right ear or just the left ear. And obviously sound has more bilateral representation because, it's split. So I don't think that would be as clean an experiment, but I bet we could design something with, we need eye tracking. It'd be complicated, but where you actually prove you presented to the right occipital lobe. But that's probably easier as an outpatient. And we have IRB approval now, and we're getting the research tools to do work with patients with neuropace implanted. So obviously that's much more limited in terms of where the electrodes are, but potentially as a partial piece of added information to your overall picture, if we get a patient with an electrode in a strategic location, we could do an experiment like that, or even just bitemporal or I don't know. Anyways, the other thought was similar thought to the last one, but with SEEG patients. So obviously ECOG is great, and it tells you all the surface stuff and passing information. But I wonder, I found when you presented that stuff about the parahippocampal gyrus being part of the visual network, but not necessarily the auditory semantic network. I think that's really fascinating, and I don't fully understand it because I feel like the hippocampus has to be involved in all of them because you got to retrieve some memory or some. So I wonder if you replicated some of these experiments with patients with SEEG in deeper locations, if that may sort of round out your overall model, because you could still, if you have a consistent timing that's showing across patients, in terms of 100 milliseconds, 300 milliseconds, or whatever it is, if you find that the hippocampus lights up at least before, after, or where it is in the sequence. I don't know. Anyways, those are things I was thinking about as I was watching you, but really great stuff.
Yeah, I agree. I agree. And I don't want to make broad statements about all of the anterior, inferior temporal regions. I think there are probably, like, for example, the hippocampus, I would imagine, is not just a visual structure. I would imagine that's a higher level structure. But this area, the parahippocampal gyrus, to me in these studies seems to be more visual. And I don't think it's, we know, like, the parahippocampal place area, the fusiform gyrus, obviously immediately adjacent, has high level visual representation. So I don't think it's off the wall to say that this area, the parahippocampal gyrus, contains a high level visual representation, but obviously that doesn't apply to all the other ones. The SEEG data, I totally would like to study those patients as well. We just have to, we have to take what we can get. And yeah, a lot of them probably will actually have depth electrodes placed around these medial temporal structures, so that we might be able to get some good data on, actually.
They're much easier to work with too, because they're sitting there on the floor, they're bored, they're just waiting to have seizures, you don't have the time constraints. And most of them, in my experience, are very, very willing to participate in research. So.
Yep.
Well, that was wonderful, Bill. I really liked it. I'm sure there are lots more questions, but as we are over the hour, I'm going to let people go. And I assume that they can email you if they want to
Please.
follow up with anything.
Please, be happy to.
All right. Thanks for taking the time. Have a great day, guys.